Okay, so before we start, I know this hand thing is not working, but can you please just raise your hand if you work with Java so I know how to steer this presentation? Okay, I see quite some Java developers here, so that's nice. Okay, so I am Eroll Gorci. I mainly work with Java. I am a Java tech lead in Kinakarta, and I've been working with Java the better part of my career, so a few years now. This topic will be all about Java 21, and we will see first how Java evolved, and then what do we get new in this release. So Java is known for being a reliable language, so to say. That's why it's not uncommon to find Java in the enterprise world applications. Even though it's a reliable language, it had its bumpy roads when it comes to from its first release in 1996 till now. So in the 22 release, so 21 is the latest supported version. The reasons why Java had a bumpy road was because it wanted to save its reliability and also its backwards compatibility. But this all changed in 2017 when Java moved away from feature-based release model to a more time-based release model. So they plan to do a release every 6 months, where from those releases every 2 years we will get an LTS version. LTS stands for long-term support, so meaning that everyone who wants a stable and reliable versions could switch from one LTS to another one, but all the developers who were waiting for features didn't have to wait for 2 years to get their features back. So in Java 21, there are quite some features introduced, but an emphasis is more on the Loom project. So it's a project within Java, which is trying to bring forward or rethink how we do concurrent programming. I'm going to go through a few features, so we don't have time to go through all of them, but I will briefly touch on some of them, and then we will spend most of our focus on virtual threads and also structured concurrency. Let's start with the cherry on top first. So everyone who looked at Java at first, or if you did Java in your university, you saw Java's main method. So it's a very well-known main method for its boilerplate code. So there are a lot of things going on for just a hello world application. And we can finally say goodbye to our public static void main string array args, and we can just say hi to main method. The reason why this happened is because Java introduced, in this version, it introduced a name class and also an instance main method. Even though this is a preview feature, so it's not a fully fleshed feature yet, it's a feature that's going to be a standard feature in the new versions of Java. Meaning that even though it's a small change, this tells a lot about where Java is headed and what are we going to do in the future with Java, so how is the future going to look. And this can briefly tell us that we are going to have a more switch of focus from big enterprise application to also smaller applications that we can run. Okay, so after the unnamed classes and instance main method, we have pattern matching for switch. Pattern matching is not a very uncommon concept for us, even though we didn't call it pattern matching. So we had instance of, and basically pattern matching, what it is in an essence is trying to match through some certain characteristics. So in instance of, for example, in this simple example here, we're trying to see if an object is a string. And if this condition is fulfilled, then what we do is we just cast that object into a string and then we print it out. So here you have a nice Easter egg also, because this is another feature in Java 21, which is a preview feature. So replacing the string here this is called, wait, what is this called? I forgot. This is called string templates, yes. Okay, So this was how we did casting before, or how we did pattern matching. But in Java 16, we had pattern matching for instance of. So now what we can do is we can directly just declare the variable inside the if, and then we don't have to do all this type of casting. And we also handle other cases. So for example, if we have a null on the object itself, we don't need to do extra checks inside the if to just cast the object. This was when this was introduced for instance of, but what happens if we have to do a lot of if checks? So let's say we have an object back, so we have a value and we want to return the string representation of that object. Till now, what we had to do is we had to do all this sort of nested ifs, even though the pattern matching for instance of it eased out the pain a bit because we don't have to do also null checks inside the ifs, which would be terrible. But now we do have pattern matching for switch. What we basically have is we can pass an object into a switch, and then we can automatically detect the type of that object inside the cases. This is not valid only for casting objects. This is also valid when we are dealing with other type of pattern matching. For example, if we have a sealed interface, which is an interface which we declare or which we restrict the classes from which it can be implemented of, we could also include pattern matching here, and this is also exhaustive, meaning that if we leave any of the cases behind, we'll get an error saying, look, you left this or that behind. Okay, so that was pattern matching for switch. And in a similar context, we have record patterns. So records are just some small type of pojos in Java, or a new reworked pojo, I would like to say it like that. And what happens here is with record patterns, it's still the same. So we're doing something with some certain characteristics, but in this case, we get the opportunity to decompose a record. For example, here, so this is the person record, and also which contains the address record, and then we can decompose this completely, and we can access its methods here inside the if. How pattern matching works is we match to compare to a type and not to a name. That's why I purposely named this as X, Y, and Z, because it doesn't matter what we name it as. It just matters if we have the same type or not. This might look simple and not that impressive, but this can help a lot when it comes to having complex objects and also having a lot of nested objects inside one another. Okay, so this was record patterns. Next up is the star of the show, as I mentioned in the beginning, and that's virtual threads. Virtual threads are basically a new lightweight thread. How would I like to approach explaining what virtual threads are and why are they needed is a more problem solution oriented presentation, so let's do that. Okay, we have here a simple example. So what we do is we just build a request. So we have a method to get the user by name. We build the request, we send that request to the user service, which will make an API call. So it's an NIO call, it's a blocking code. And then we return the response. So we basically just build a JSON object, and then we return that immediately. If we look at what CPU is doing during this code execution here, is at the first line, we have 100% code, we have 100% CPU utilization. So meaning that the CPU is working and then the code is being executed, and it's a fairly very fast execution because it's happening on the CPU. So the time that takes for this to execute, it will be around 100 nanoseconds, let's say that. Okay, so on the second step, we have a blocking code. So blocking code meaning that while we're executing on our service is waiting for a response or is waiting for some infrastructure to reply back to it. Meaning that our CPU is idle, so it doesn't do anything. It's just staying there and waiting. And this is a kind of a waste of resources when it comes to performance computing and also utilizing all the resources that we have. And on the third step, what happens is the CPU is still back up, so it's on 100% again, and it's fairly fast also. If we do the math and if we see how much did we use our CPU during this whole execution, so this whole code execution, we can see that we use the CPU 0.0001% of the time, which is quite a waste of the resources. This problem is not new, so this is a very known problem in the software engineering world, and that's why till now we've come up with different solutions for this problem. So let's say we want to have 100% utilization of our resources, and we want to launch a lot of executions of this code. How can we do that? In Java, we usually use threads. So Java comes with threads by the box from the first version, so it has concurrency built into it, or concurrent programming where you execute multiple stuffs at the same time from version 1. So if we do the math here, we see that in order for us to have 100% utilization of the CPU, we need to spin up 1 million threads. And spinning up 1 million threads, it's almost impossible. The reason for that is because to create one thread, it will take us 2 megabytes of memory. Why this happens is because Java threads are just a thin wrapper of the OS thread, so of the kernel thread. And every time we spin up a Java thread, we spin up a kernel thread. So to spin 1 million threads, we would need 2 terabytes of RAM memory. So 2 terabytes of memory, which is almost impossible to have in a standard machine. Okay, so this problem, even though it was not kind of fixable, or it was not quite fully fixable with threads, we had other approaches on how do we want to fix this code. Another approach or another initiative that was for like 10 years now was trying to do something on asynchronous programming. So that's why we have asynchronous programming, reactive frameworks, and other things like this. The idea behind asynchronous programming and also reactive programming is not to spin up a thread for every request that we make, so not to spin up a thread to execute that same code every time, but what we do is we try to make multiple requests per thread. And how that happens in Java, it's quite complex because Java is built more around threads. It is not very native on asynchronous programming. We do that with a completable feature. So basically, we do create some atomic lambdas which will interrupt the code execution as soon as there is some blocking code. And what happens then is we then have to wait for the callback, which will start the new process again. So here, to then apply, that is kind of the callback of this function. This works fine in the meaning of it has its drawbacks, but one of the worst things about this code, especially in Java, is that it's very complex. So if we check at this code here, this is a very imperative way of programming. So it can be described as boringly simple. So you have building the request, sending the request, getting the response. So it's that simple. But when it comes to asynchronous programming, the complexity rises. It's way more complex to write. It's even more complex to read, especially after 2 weeks that you have written it. So Java, for 10 years now, is trying to rethink how we do concurrent programming. And virtual threads are some of the features that Java is introducing with this effort. As I mentioned, the virtual threads are part of Project Loom inside Java. And this is kind of the main area where they are going to make the improvements. So virtual threads are lightweight threads. What I mean with lightweight threads is that when we create a virtual thread, we are not creating a kernel thread anymore, the one that was taking up to 2 megabytes of memory. What we have here is we have the fork join pool, which is basically the executor inside Java, which pulls the threads. So till now, to kind of fix the problem that we had with not being able to create thread for every request, what we did is we pooled threads. So we created a pool of threads, and then we use them and we release them. But in this case, what we're going to do is we're going to have a lightweight thread which is going to stay on top of that pool. And then let's say we start to execute that code. As soon as these workers here are basically, you can look at them as the platform threads. We start the execution of the code. We go to a place where we have a blocking code, so a call to the database or a call to an API, which will take longer. And then what happens is Java, these virtual threads are surrounded by an object called continuation object, which is not accessible for us, but it just works in the background. And what we do is we yield, from that object, we yield this virtual thread. And we move the whole stack from the worker itself to the heap memory. And when we move the stack to the heap memory, what happens is the other threads are freed, and we can use them for other processes. As soon as the response is back, what we do is we return back the virtual thread inside the worker. So also one thing to keep in mind is that a virtual thread is not also tied to one worker. So at the when it was on the heap memory, if worker 1 was occupied, it could move to worker 2, worker 3, or any other worker. So this is basically how virtual threads work in underneath, and this will allow us to do a lot of more concurrent programming and being more efficient in it. Virtual threads are built, so what we need to keep in mind is that virtual threads are built to help us improve the performance of code that has blocking code on it. So we cannot, when compared to platform threads, we don't get any benefits if we use them in non-blocking code. The reason behind that is because all this moving of the virtual thread to the heap memory and then back to the platform thread, it's expensive. And in cases, it can also degrade our performance if we're not dealing with blocking code. So the next final feature that I'm going to present here is structured concurrency. This is also part of Project Loom. So this is also kind of the same initiative with the virtual threads. In this case, what Java is trying to improve with structured concurrency is, till now we had the problem of not knowing when a thread or when an execution of a task in a thread is finished or it's failed or stuff like this. So let's say hypothetically we have 2 long-running tasks, and both of them take around 15 minutes to complete. Till now, what we did is we started those concurrent tasks. And then if the first one or the second one failed within a minute, we still had to wait 14 other minutes for the second one or the other one that did not fail to complete in order for us to know that, hey, look, one of them failed. In this case, what we do is we have the structured concurrency, structured task scope here as a class, which also implements the auto-closable object. That's why we can wrap it in a try, because as soon as all the processes are finished, it will close itself, so that we don't have any leakage or something like that. And inside the try, we can see that we have 2 tasks, task 1, task 2. And we do fork them, so we start both of the tasks, and then we join and throw if failed. So what we do here is we wait for the processes to return something. And this will return as soon as one of them fails or as soon as both of them are completed. So in case both of them are completed, we just continue down the path and we do get back all the results from both of them. But if one of them fails, then we throw an exception. And this is very good because it allows us to manage more our concurrent tasks. With structured task scope, we don't have only shutdown on failure, but we also have shutdown on success. So let's say you're trying to find a hash of some kind, and then you're starting 20 processes at the same time. and you want to terminate all the processes if one of them succeeds on finding the hash. So that's also another thing that we could use this for. So one thing to keep in mind is that with structured concurrency and also virtual threads, there are not perfect solutions that we can just take and sprinkle them everywhere and then we will get perfect results. But it's good to know what's happening and how this is happening and when this can be beneficial for us. Even though we might not use them on our day-to-day coding, because we do use bigger frameworks like Spring, Quarkus, and other frameworks. Those frameworks have already built something with virtual threads. They have already built something with structured concurrency, and it's always better to know what's happening underneath the abstractions. So this was it. It was a quick presentation because we could go even deeper into more details. But I hope that this was kind of informative for you, and if you have any questions, please ask them, or we can also continue the discussion on the coffee break. So.
Thank you, Eroll, for your presentation. That was indeed a very quick overview of a lot of complex things. So I am wondering what kind of questions does the audience have, and I think we might have a bit more time for questions now since you are very quick with your presentation. So if someone has any questions, please put your hand up and we'll get the microphone to you. Yes, over here in the third row on the side, please.
Great presentation. Is it working?
Yes.
Great presentation. One question. Can you give us like an example when not to use virtual threads?
Yes, that's a very good question because, as I mentioned, they are not a perfect solution to everything. Let's say that we have that we want to run. We have a complex math equation that we want to solve, and then we run that equation in multiple, let's say, multiple instances to complete it. We would not want to use virtual threads in that case because that's a non-blocking code. So all it has to do is it has to do CPU-intensive operations, and it all happens in the device. So if we spin threads, they will be way more faster than spinning virtual threads because of the overhead that I mentioned, that having all that logic inside of moving the virtual thread from the heap and back, that will degrade our performance compared to using just normal threads. And now, just to add on this, the good thing is that virtual threads are built on top of the thread API, which we are all familiar with. So it's very simple to create a virtual thread. So now we also in the executors, you can just create off virtual or off platform to just create one or the other one. So.
Cool, thank you.
Thank you for the question. Are there any other questions in the audience, whether down here or up there? Can't see quite well from the light, but
I don't see any questions. Okay, I think it's time for a quick coffee.
yes, I think that in that case we have a bit of a prolonged coffee break. So enjoy your coffee, use the time wisely to catch up with all the presenters and ask questions you might not have been able to ask before. And we'll see you back here as per the agenda. Thank you so much, everyone.